Thank you very much, Benjamin, and good morning, everyone. Thanks again to the organizers for this wonderful conference and the opportunity to give you this tutorial this morning. This is a little picture taken during the power failure yesterday morning. It's a very short hike up the hill from here. It opens up into this lovely alpine meadow with chalets, and I guess our intrepid hosts had hiked far beyond here up to the summit and then skied down. But, okay, so as advertised, I'm going to speak today about nano and optomechanics-enabled magnetometries, and since this is a tutorial, I took the opportunity also for my own interest to kind of dive a bit deeper than I otherwise would have had the opportunity into the history of the subject. And so I'm going to share some of the things that I found in doing that also with you. So the flow will go like this. I'm going to go through some very deep background magnetic torque through the ages, and then I'll talk step by step through basics of a torque sensor design and the readout, sensitivity limits, and calibrations, and then I'll present some very highly selected highlights, and then wrap up at the end with some observations about current and soon to be coming prospects. Okay, so here are just some of the, in doing the deep background, I pulled a lot of basic books off my shelf, and so these are some of the sources that I referenced in preparing this tutorial. Okay, so just going back to the very beginning, this I believe is the earliest purpose-built magnetic torque sensor, at least here on Earth. So these are the famous Magnetotactic Bacteria that were discovered in 1975 by Richard Blakemore. And what happens here is this is kind of a mud-feeding ocean microbe, and it has a built-in compass which orients it in the Earth's field so that it knows which way to swim to go down into the mud where its nutrients are. And the way it does that is there are these little invaginations here that grow these magnetosomes, so-called, that contain magnetite particles. And they're large enough and close enough together that they're dipole coupled and form a fairly stable compass needle like this. So it orients it just like this dip meter in the Earth's magnetic field. And so if you take one of these from the southern hemisphere into the northern hemisphere, it swims the wrong way. So just the numbers, so just, you know, we know now what the saturation moment of magnetite is and whatnot, and we can just calculate the magnetic torque, and it turns out that the torque on this little beastie here in Earth's field, the maximum torque is about 20 piconewton nanometers. And this, you'll see, is piconewton nanometer turns out to be kind of a natural unit for the scales of torque that we'll be dealing with. Likewise, just thinking about how stable this thing is or not, the magnetic potential energy minimum when this is aligned with the Earth's field is about 10 kBt. And that is enough to stabilize it against rotational diffusion. So you can also see here, you can, if the thing is swimming in water and you use the dynamic viscosity of water, and you can calculate a rotational drag coefficient and determine that in zero field, the rotational diffusion constant of this thing is about 0.2 radians squared per second. So without this Earth's guidance orienting it, it would tend to drift off alignment by about half a radian in a second or so. The other thing that I thought was interesting is even in the discovery paper in 1975, they were able to do good enough transmission electron microscopy on these things to actually see the flagella from the motors that propel these things, how they're attached, and now people know much more in detail what's happening in these biological motors. And it turns out here also that in so this thing is driven by ion transport across some roughly 90 millivolt membrane potential difference, and just from the energetics of that, and knowing that the thing turns, it takes about 12 ions to put the thing through a full 2 pi rotation. You can compute that the average torque that it generates is also on the scale. It's about 30 piconewton nanometers from the motor. Okay, so now there's a whole bunch of stuff that we have to skip over billions of years to get closer to our subject. So here actually is a gyroscope. So Maxwell is one of the early intellectual founders of spin mechanics, and he realized that there should be a mechanical angular momentum, or could be a mechanical angular momentum associated with current flow. I mean, at the time, they didn't know that, well, the electron hadn't been discovered, and so didn't know that it was one charge carrier that was responsible. So people realized there could have been 2 oppositely charged counter-rotating fluids in putting current through a ring, and so there might actually not be mechanical angular momentum, but he actually set out to try and test it experimentally and built this gyroscope in 1861, and there's a whole bunch of interesting history there too. This was found in some storage room later by Kapitsa at Cambridge, this thing that Maxwell had built. So that we know now, right, that the electron turns out to have an extremely high charge for its mass, and so Maxwell wasn't even close to being able to have the sensitivity to see an effect here. But other things happening, not too much longer after that. So Hutchinson and Rowland built this really impressive torsion apparatus to do the test as to whether the expectation, of course, was that statically charged rotating plates should generate a magnetic field. We do that in first-year physics problems, have students treat moving static charge as a current, but that somebody had to experimentally test that, and so this was done by Rowland and Hutchinson, and the experiment was successful. And when you look at it, the magnetometer that they built actually to do that had a nanotesla sensitivity. Okay, so one of the real historical keys to sensitive torque measurements, especially in the early part of the 20th century, were remarkable quartz fibers. So here's a paper by C.V. Boys in 1887 in the Philosophical Magazine. So what he discovered was that he essentially discovered how to make optical fibers. Okay, so he built a little custom-made crossbow that had little arrows made of straw with a little needle on the front. And then what he would do was take a piece of glass or quartz and just melt it, so get a little melted boule, and then tack a little piece of the molten glass onto the end of his straw, and then he would just trigger his crossbow. And then this thing would shoot across some long room and leave an incredibly fine glass fiber that would drape onto some like black material that he had across the floor so that he could find it. And he actually, it's remarkable going through this paper and sort of all of the things that later people spent, careers and decades going through in detail. So he actually was able to make fibers down probably to about 1/4 of a micron in diameter. He was able to make, and over, had, good control over the diameters of these things from 1/4 of a micron up to, say, 100 microns, and could make like 2.5 micron fiber that was 90 feet long or something, and quite uniform. And so people, I mean, it's interesting. So basically, there's all this stuff, and so people encouraged him to like publish this, to kind of, and indeed, so another person very famous in our field, Barnett, one can find one of his early publications actually at the end of his PhD at Cornell in 1898, was also on investigations on this kind of Boisian quartz fiber. And fibers like that, of course, were used in the Einstein de Haas experiment. Okay, now, so we've kind of moved from beyond the quartz age. So, and one of the things that motivated that was, oh, actually, did I? Nope, it's coming later. Okay, the I have yet to show you how, you know, attaching the sample to the fiber. This is a big challenge, and the way people did that with these quartz fibers was incompatible with cryogenic experiments, and so people had to move to different materials to do this. And so related to a little bit to the superfluid experiments that Adrian talked about the other day, Andronikashvili made this famous torsional oscillator to measure the superfluid density of helium-4 originally, and that he wasn't using quartz there, he used phosphor bronze wires, so you can attach those in ways that it won't separate when you cool it to low temperatures. And then those methods were evolved, and again, this is out of the group that made that famous Kostelis-Thouless measurement. So there was an earlier paper in 1975 where they introduced this torsional oscillator scheme. So they called them androns as an homage to Andronikashvili, and the state-of-the-art material for these things that you would go in the machine shop and make were made with beryllium copper. And then the same people, Repi and company, in mid-1980s at Bell Labs, they explored silicon-based, micromachine silicon-based torque sensors, and already showed it was possible to get quality factors up to 10 to the 8th. And so we've kind of transitioned through the 20th century, I think, from quartz to bronze and then silicon age. We're still in the silicon age in the early 21st century, as you'll see. Yeah, just to see, there's no time to go through all the details. John Moreland wrote this lovely review article that was published in Journal of Physics D in 2003, and there you can see it captures the application of silicon. In our group now, we call them torsionators, as applied to ferromagnetic measurements. Okay, so what are we actually dealing with here? So with these torsion fibers, when we twist them under a torque, basically what's happening is internally interatomic forces are arising to cancel the external applied torque, and that will, if it's a static measurement, determine a new equilibrium angle of twist. It can be thought of as a pure shear being applied along the torsion rod, and just geometrically with vector addition, one can see that a pure shear on a cylinder on the surface and in the interior resolves into orthogonal compression and tension. And there's a fun demonstration that one can do in materials that have comparatively small tensile strength compared to their compressive strength. You can kind of see for your own eyes like how this resolves. So I don't know if anyone, I brought 2 pieces of chalk. Someone want to twist? Just like, yeah, firmly grip the 2 sides and then give it a twist until you overcome the tensile strength of it, and it should have fractured kind of in a little spiral pattern. Yeah, and so that. Yeah, so it looks like this, the fractured chalk, and of course this is a really important thing in structural engineering. Okay, so to figure out what the spring constant is of this, essentially, we just have to integrate this shear force over the area and put in the shear modulus. So we'll find at the end of the day for a cylinder that the torsional spring constant is proportional to the shear modulus, and then to the fourth power from the shear stress and the torque. They both scale with distance from the center here, so it'll go like the fourth power of the diameter divided by the length. And in rectangular shafts, it's a little more complicated because on the surface you don't get a uniform stress like you do on a cylinder, but that was all solved in the mid-19th century and has been summarized in various texts. So in the end of the day, we work with a formula where the fourth power for the diameter resolves into the long dimension times the short dimension cubed, and then with some factor correcting for the aspect ratio. And so just looking at some numbers, if one takes for a long quartz fiber, say that boys could have made 2.5 micrometers long, in diameter, and 50 centimeters long, we get a torsion spring constant on the order of now 14 piconewton millimeters per radian. And so if we imagined that boys tried to do an experiment to measure, like if he had one of these magnetotactic bacteria and mounted it on the end of one of these torsion fibers, the twist that you would get on a fiber like that would be on the order of 1.4 microradians, which, to put that in a scale, is that big or small? Well, it's not really big, obviously, but it's not ridiculously small. So for instance, we can easily resolve angular changes just eyeballing on the order of a milliradian. For instance, if you look closely at the minute hand on the clock there and how much it moves with every second ticking, that's about 1.7 milliradians. Okay. And Boyes, when he was starting to make his torsion measurements, so the magnetic sensitivity was just a nuisance for him. So he had to sort through a whole bunch of different materials so that he wouldn't have huge unintentional deflections of his torque sensors from magnetic fields affecting the materials that he was using to put them together. One of the large important applications of torque measurements in magnetism through the 20th century and continuing today is for determination of magnetic anisotropy. So here, if we imagine that we have, in the simplest case, a specimen that has a uniaxial anisotropy, so the magnetic energy is going to vary like this as the angle between the field and the moment is changed. The moment and the easy axis of the material. The variation of that energy with angle determines the torque on the moment with angle just by differentiation here. And so you can make a basic device to look at this, to characterize this, for instance, by having a sample in a magnetic field that can be rotated that has just two dials on it. So one here tells you the angle that you're trying to set the sample in the magnetic field, and then the other dial is going to tell you a relative twist along this torsion member between the set position and the equilibrium position that this comes to, and that will simply map out directly this anisotropy energy. So I took this image from Cullity's textbook where he notes that looking around labs in the world in the mid-20th century, the devices are all homemade, and their design varies almost from one laboratory to the next, and that is still true, basically, in the work that we do. So those are static measurements, as we've already seen in many talks earlier in the workshop already, that often now measurements are made instead with an AC method, so you can take advantage of a resonant enhancement of the amplitude of response to a given strength of torque. And again, Boys also noted this, that you know, they're very sensitive to oscillation. So here then, to turn this into a torsional resonator, if we imagine in the simplest case we have some moment of inertia that's separable from the torsion spring, then we will get a fundamental resonance just at a frequency given by the square root of the spring constant divided by the moment of inertia. And then in the simplest case, if we drive with a resonant torque at this frequency, we'll get an enhancement of the amplitude of response by the mechanical quality factor. And indeed, this approach was already used by Einstein and de Haas in their original measurements. So this is some data from the paper driving through, changing the frequency through the resonance. Okay. So here, just to share one more thing about Einstein and de Haas. So this is in a paper by Frankel where he recounts Einstein's summary of again, one of the keys here is how you get the specimen onto your torque sensor, and the iron cylinder for that experiment had to be very well aligned with the quartz fiber, and that was done by attaching it upside down like this. They would heat up the iron, put a little dab of rosin on there, and melt that, and then just insert the quartz fiber, and surface tension would pull in the fiber and self-align it centered and straight, and then they would cool it, and then it would be attached. But again, of course, if you try to do a cryogenic experiment with this, the rosin would just delaminate from the iron, and that wouldn't be so good. Okay. So now, we clearly want to do something better than just eyeballing the deflection of these things to make a sensitive readout. So now I want to go through, I'm going to just concentrate here on optical detection, although there are many other schemes that one can implement. So let's step through that. So viewing a dial, of course, as I've mentioned, so that's kind of the jumping off point. This is a picture of my maternal grandfather's World War I compass. So let's say this has on the order of 10 milliradian resolution, just viewing the dial. The improvement on that, if you can just increase the lever arm, so many measurements have been made, including the Einstein and de Haas, by just attaching a mirror to the fiber and then bouncing a beam off it and measuring the deflection at some larger distance. Boys already did that with about 100 microradian resolution. If you replace your eye with some kind of electronic detector, mid-20th century devices often were implemented this way. So you have your mirror, your beam bounce, and then you would make a simple optical position sensitive detector by splitting the beam in a mirrored prism and then measuring the reflections on the two sides. And when the thing twisted, you would get an imbalance there of the signals on the two photodiodes, and so that could quite easily and routinely resolve microradian deflections. So beam bounce, it's still used a lot in atomic force microscopy and so on. It's powerful. Rugar et al. Showed that you could do better with fiber interferometry. So here's from their very nice paper in APL in 1989, where characterizing the displacement sensitivity. Apologies that this scale is very difficult to read. So this is noise spectral density in angstroms per root hertz, and above about 100 hertz here, they've got 10 to the minus 3, so this is about 10 to the minus 13 meters, 0.1 picometer per root hertz displacement resolution, and then depending on your the lever arm and the device that you're looking at, you can calculate the angular sensitivity. We get correspondingly similar displacement sensitivities in simple free space so-called implementations that we use. So this is from some of our silicon nitride torsional resonators, where we just make a low finesse interference cavity between a little mirror that's mounted to our torsion fiber essentially, and twisting with it, and just a substrate nearby underneath. So the limitation of this kind of implementation in interferometry is really just from the fact that each photon is just going in and out once. It's a very low finesse cavity, and just picking up one increment of phase shift from any relative displacement. So here one can get a lot more mileage again out of interferometric detection by adopting the methods that were developed for gravitational wave detection. Here is the earliest paper that I could find in the gravitational wave development that incorporated a Fabry-Perot cavity in an interferometer in order to enhance the displacement sensitivity. So here the idea is, again, it's very basic, that you want to multiply the phase shift that's resulting from some relative displacement of a moving mirror and a fixed mirror by having the light bounce back and forth many, many times before it escapes for you to make your observation. So this is actually very difficult to do in something like a gravitational wave detector because what turns out to govern this, so the number of round trips isn't just determined by the optical cue, right? If you have a very long cavity, your mode number is very high if it's long compared to the wavelength. And so the amount of energy stored, and then correspondingly the amount of energy lost per round trip, is the mode number times the number that you would just naively calculate if you were looking at something like this with a mode number of 1. So the thing that actually governs the number of round trips is the so-called cavity finesse, which is just essentially the distance between neighboring modes in frequency divided by the optical line width. So actually to get a big enhancement in a 4 kilometer interference arm, you need extraordinarily large optical cues and extraordinarily narrow laser line widths also to do that. Even in this first experiment though, so they had a sweet spot that theoretically, with their cavity finesse of 220, this was a small scale kind of laboratory implementation, they theoretically could have got 140 times improvement in the displacement sensitivity They were able to demonstrate a 25x improvement at a sweet spot here that happened to be at about 80 kilohertz in this implementation. So, but again, that on this scale, that was already mirror displacement down on the scale of 10 to the minus 17 meters per root hertz. Fortunately for us, it turns out that it's easier in a way to implement something like this in a nano cavity sensor because it's so small. Essentially, you can make a cavity where the mode volume is on the order of a cubic wavelength. So it's like a mode number of 1, and so the finesse factor is essentially like the cube. For torque measurements, this is the photonic crystal cavity with little Bragg mirrors here that we use in some of our measurements. This was designed by Aaron Hritchu and Paul Barclay in 2013. The idea here is, this is an implementation reported by Marcelo Wu et al. In 2014. So here, this will be our torque sensor, and then we're detecting the displacement with a little photonic crystal nanocavity here. The idea for confining the light and having this thing able to twist is to taper the aspect ratio of the holes in the photonic crystal adiabatically until in the center of the cavity you can have a sufficiently large aspect ratio ellipse that you can actually cut the cavity, but the photons don't know, right, that you did that. So you have a Bragg mirror on either side, and you have a high electric field concentrated in this gap that is free to move when some torque acts on your torsion member here. And there's a throwback to Boys here, so the way devices like this are read out currently, you can see we don't have any integrated waveguide here to couple light in and out of this cavity. So what we do is we use a dimpled tapered optical fiber that is brought into close proximity with this device, and then when it's within an evanescent length, then you can have light leaking into the cavity, and you can monitor the change in the transmission through the fiber. So this, Paul Barclay, who we collaborate with on this, he was one of Oscar Painter's first grad students at Caltech, and actually is the pioneer of this application of optical fibers for coupling to photonic crystals. So what does that look like in practice here? So here's a device. Here, excuse me. Here's the optical transmission through this device. You can see that the optical quality factor in this case was about 12,000. And what's plotted here is just the Brownian motion of this device. There are several mechanical modes here that one sees versus frequency, and plotting also the displacement just as a function of the laser wavelength. So primarily here you get signal from the slope, right, proportional to the slope of the transmission curve as you're shifting it back and forth dispersively, from slightly changing the cavity resonance with the motion, but there are also here so-called dispersive couplings, because in this case there's also some change in the Q associated with the motion. At the end of the day, here this boils down to about 10 nanoradian angular displacement resolution on this kind of short. So in this structure, this part is anchored. Yeah, so the torsion rod here is just this one. In this one, it was just a T-shaped device. Okay, so that the Brownian motion there is our routine key to calibrating the sensitivity of these. So by equipartition, you will have a half kBt in the potential energy of this mode. So if you integrate over the entire mode, you should get a root mean squared angular displacement that's just proportional to kBt divided by this torsional spring constant. When you look at the entire shape of this angular power spectral density versus frequency, it will look like this. But then by integrating it, and you can set the scale height here just from the total integral under that. So this is what some of these look like for typical devices that we work with. And so you can put a scale on here, and you can convert from also the microradians per root hertz in this case of spectral density to an actual physical displacement by how long your lever arm is, how far your spot is off center to do this interferometry. Okay, and so that looks like this. As these devices become less and less like just a simple mass spring with a clearly differentiable torsion spring and moment of inertia, you have to do more in-depth analysis to actually do a quantitative calibration here. So for devices at this level, you can still do an analytic determination of the torsional spring constant. That's been reported here out of Craighead's group at Cornell about 10 years ago. And so here, applying this formula, it's the same shape structure that we're using here. And this is how we get, at the end of the day, an absolute scale here of displacement for calibrating our device. As the devices become more complex and you begin to get elements of hybridization of pure torsional modes with flexural modes, then typically you have to go into finite element modeling. So here you can then get a displacement profile of the mode from your finite element model and compute the potential energy, for instance, at the position of maximum displacement by integrating over that to get an effective torsional spring constant that you would then use in the calibration. So this is what something like this looks like for a device with the nano cavity readout. You can see you get very nice signal to noise on the Brownian motion. And then as you integrate, right, because the Brownian motion is averaging incoherently, that at the end of the day, the signal to noise that you get will scale like the ratio, as the Q factor increases, the driven signal will increase like Q, but the height of the Brownian motion will only increase like the square root of Q, so that your signal to noise at the end of the day, if you're limited by the Brownian motion, will scale like the 1 over the square root of Q. So it will the minimum torque that you can measure will scale like 1 over the square root of Q. So here, after all these centuries of, well, century or so of progress with this Barclay device, at the end of the day, we wind up with about 1,000,000 times higher torque sensitivity than with like that early Boisian quartz fiber. Now, yes. Yeah, this was measured, this device is actually operating in air at room temperature. Yeah, yeah. So the mechanical quality is not great. It's limited by air damping. And then there are other nuances here. One can look at the stress distribution in the finite element model and realize that there are other potential energy factors that need to be taken into account to make a fully quantitative determination here of the displacement. So there's essentially a systematic error that one can easily miss if one doesn't look at the fine details here, because in the nanomechanics, even though the displacements are small, with the frequencies being relatively high, the accelerations can actually be huge. So there are internal stresses developing along the beam here, and additional stresses in the torsion bar that are required to keep the mass of this paddle attached, essentially. And so this motivates interest in alternative methods of calibration as well. Ultimately, a metrological approach to get rid of the systematic uncertainty here would be to actually use the angular momentum of light to do a calibration. And here, this is a famous experiment by Beth in 1935, actually measuring the angular momentum of light by mounting a wave plate on the end of a torsion fiber, and steps towards implementing this on the nanoscale have already been made in Mo Lee's group at Minnesota, where they have a birefringent waveguide attached to a torsion beam, and can begin to measure the torque just from change of polarization of light going through there. So this ultimately could become metrological by layering on a single photon source and then actually being able to countably monitor the angular momentum impulse going into the device. Okay, so now just some highly selected highlights of things that have been done with torque magnetometry. So here, I think, is a highly underappreciated experiment, the detection of paramagnetic resonance just by angular momentum pumping. This is the Alzetta and Ascoli work that came out 50 years ago in Nuovo Cimento. So the idea here is it's an Einstein de Haas kind of geometry applied to magnetic resonance. You have a sample, in this case it was the diphenyl pi hydrazole DPPH, this standard ESR specimen on the end of a torsion fiber, and you have a polarization induced by a DC magnetic field that's parallel to the fiber, and then when you pump this on resonance and have a reduction of the longitudinal moment, that corresponding angular momentum impulse makes the fiber twist. And when you run the numbers here, pumping close to saturation, you can get a gigantic torque on the order of 4 piconewton millimeters per milligram of the DPPH here. And the reason why this is so large is because the T1 of the spins is relatively short in this material, so you can actually have many cycles of the spin relaxation during one period of the torsional oscillation. after MRFM began to be developed, this group was inspired to go back and implement this measurement again on the micro scale with the micro cantilever. So now we have a tiny little piece of DPPH on the end of the micro cantilever, and what they did in this 1996 paper was do the pure torque measurement by the angular momentum pumping, and then also a corresponding magnetic gradient force measurement in the kind of Rugar style here to show that they could get comparable signals from the two approaches. Then there was this lovely experiment related to that 10 years later out of the Moreland group at NIST in Boulder, where they measured the G prime for permalloy by, again, an Einstein-de Haas measurement. So they had a strip of permalloy on a cantilever, and they, in this case, the torsion axis is parallel to the base of the cantilever, and so changing the moment parallel to that axis gives you the Einstein-de Haas torque, which then they could use to determine the G prime of the permalloy. This was in poster session 2 last night. So the current record for optomechanical torque sensitivity is out of the Davis group at the University of Alberta. So Paul Kim makes these beautiful devices where there's a microdisc resonator coupled to a beam that's on the end of a torsion arm where they can mount a sample here, and running this in a dilution refrigerator, they were able to reach a minimum torque sensitivity on the order of 3 yocto newtons per root hertz. Sorry? Paul. 2 microns. Yeah. The resonant frequency, what was the resonant frequency, Paul? 14 megahertz. Yeah. And yeah, of course, we've seen also this amazing experiment where, so another kind of extreme in materials that couldn't have been foreseen back in the days of Boys, or things like carbon nanotubes to make a torsion member, and in this case, one that actually behaves like a mechanical vacuum for certain transitions to implicitly have the sensitivity to single angular momentum impulses from single spin flips. Okay, now where are we at? So we've been through these phases of materials refinement: quartz, beryllium, copper, silicon, carbon nanotubes. All the geometries are fairly traditional. We've had extensive control over miniaturization. So what are some of the prospects? Well, now we're entering into an age of I think, really incredible opportunities for creativity in designing different structures. So it's possible to do all kinds of programmed design, self-assembly of structures based on DNA. Here we can see some devices that have been made that incorporate nanoparticles. It's almost like the beginnings of making a synthetic version of a magnetotactic bacterium. There much has been learned about the torsional properties of individual molecules. So again, for DNA, one finds this typical scale of piconewton nanometers of torque. The synthetic chemists, basically, some of them at least, promise that they can make anything that you can sketch out. So it's also interesting just to look at torsional stiffness of individual polymer bonds. So here's just the energetics of the energy in a ethane-based polymer bond as a function of angle. So here you have two sets of 3 hydrogen atoms like this trying to twist, and if you work from the curvature here just to work out an effective torsion spring constant, it's on the order of 100 piconewton nanometers. That's just for a single bond, so of course you can make something much more springy by having it longer. These numbers, perhaps not surprisingly, turn out to be not insanely different from what you would estimate just by scaling the continuum elastic models down to molecular size. As we began to see in David's beautiful talk yesterday, there are really interesting prospects also for torsional devices that come out of this membrane in the middle approach. So here's a proposal from Jack Sankey's group at McGill to use something related to that, where it's just a small tethered membrane that's also in an optical cavity, such that at the end of the day, the spring constants on the membrane will be dominated by the optical spring forces. Those are dissipation free. And so here in this proposal, they estimated the possibility of, for a torsional mode, actually being able to reach a mechanical Q on the order of 1 billion. We saw mechanical Qs of 1 billion already yesterday, which is amazing. But another thing that's extremely powerful here is the fact that once you're in this regime of being dominated by optical spring forces, the frequency is tunable, right? And so there are all kinds of things that one can then also layer on to the detection, parametric amplification, nonlinearities. So where are they at? So they have actually begun to make some of these tethered membranes, and also in Simon Grobelacher's group. So they've got, Qs of tens of millions so far, and Grobelacher's group has characterized the force sensitivity of these. No one's done torsion measurements yet, to my knowledge, but here we're down in the 10 attonewtons per root hertz regime. There are interesting proposals for optical trapping. Again, in the posters, there's this lovely idea of using Meister levitation for this kind of thing. So lots of prospects for levitated particles. Here, who knows, there's a long way to go here, but in this proposal, it was estimated that one could measure torque on a non-spherical nanoparticle levitated down to the order of 10 to the minus 29 Newton meters per root hertz. So that's another 100,000 times smaller than currently Paul Kim's amazing device. And again, in this torque domain, things like parametric amplification, I think, have been underexplored. Here's another famous Dan Rugar paper for the first time implementing mechanical paramagnetic, mechanical parametric amplification in a cantilever, and that was ported to a torsion device in Craighead's group about 10 years later, but there's not so much that has been done in this. This was just, in both of them, they were electrostatically, parametrically pumped, but I think this is something where there's a lot of untapped potential again. And then finally, as we move into this seemingly ubiquitous new era of additive manufacturing, this also, I think, completely opens up possibilities that people like Boys and all those early pioneers never would have dreamt of. So in this recent science paper out of Wegener's group, they designed this clever mechanical structure. So now they're jumping off from other non-mechanical metamaterials into this new untapped domain. And if you look at what they've achieved here, really, so this is something that has a first order direct coupling between the twist and the length. So in this old-fashioned way, so it was de Saint-Venant who first computed this solution for twisting of the rectangular beam. But again, here fundamentally, we only get twist if we if we twist, we don't get a length change, and we don't get any twist if we push on it. But here, when you twist it, it shrinks or grows, and vice versa. If you push on it, it will also twist. And so this just has, I think, very interesting possibilities for getting, I mean, something that I didn't talk about was with the Barclay device, the way it's actually designed, if you make it perfectly, it won't have any first order coupling between the twist and the optical mode, because it's just symmetric like that. And it still works beautifully, it turns out, because when you use this tapered optical fiber approach, you can split the symmetry just by where you couple in the fiber. And so that's a nice kind of flexibility that you have with that tapered optical fiber approach. But here you could actually design in many more, for instances, a first order coupling. Okay, so that is it. And yeah, thanks for your attention. Wow, with Tor, really? Okay. Is
you're right. It's a force measurement. You use the gradient of field. Yeah, you're right. You're right.
okay. Still, thank you. Yeah, I should look that up, because you know all those things. Like, you.
But I think he used a torsion to detect the force.
Yeah, just just in case not everyone knows. So again, Olivier was one of the first physicists that I ever met who actually knew about these experiments by Zavoysky also during World War II, like for actually doing detection of magnetic resonance through electromagnetic induction before Bloch and Purcell and whatnot, right?
Actually, he used Zavoysky. I mean, yeah, it was the beginning. Actually, it was the beginning of microwave, and actually, they had a big issue with amplifier and how to amplify the signal. And I mean, it's very. I mean, they use what is called a marginal oscillator, so it's very close to parametric amplification.
Yeah.
To actually detect the signal, which was key.
Yes, so the the question is what's the relation between the mechanical frequencies and the Lando Lipchitz Gilbert damping? So the damping, I mean, they're on a similar order. I mean, usually the damping is faster still than the mechanical period here.
Is there a
The